Okay, so hello everyone and welcome to the week 4 tutorial examples. So we started with the first example. It's going to be about the rolling process. Just remember that here we're going to talk about the bulk deformation processes at the beginning. So the three examples we're going to have first is going to be about the rolling, then we're going to have the forging, then ending up by the extrusion process. So the example we have from textbook is example 15.1, and this example is saying that we have 300 millimeter wide strip of 25 millimeter thickness is fed through a rolling mill with two powered rolls, each of radius of 250 millimeters. The work thickness is going to be reduced to 22 millimeters. Remember, it was 25. It's going to reduce to 22. In one pass at the roll speed of 50 revolution per minute. So now we have the dimensions of the strip. We do have the RPM value, and we do have the reduction in the thickness. The work materials have flow curve defined by the value of the K to be equal to 275 megapascal and the N to be equal to 0.15. And the coefficient of friction between the rolls and the work is assumed to be equal to 0.12. Now, we need to determine if the friction is going to be sufficient to permit the rolling operation to be accomplished. If so, then calculate the roll force, the torque, and the power. So if you hadn't went through the theory of the analysis for the rolling process, you're not going to be able to answer this question, so that's what we're going to do next. So let's start to do the basic analysis for the rolling process. Okay, and the first term we're going to learn is going to be about the draft. So the draft in the rolling process is the difference between the initial thickness minus the final thickness. And this will tell me that this value is, in our example, is going to be 25 minus the 22, which is 3 millimeters. The reduction is a draft expressed as a function of the starting stroke thickness. So basically, it's going to be equal to the draft divided by the initial thickness. D is draft, TO is starting thickness, TF is final thickness, and the R is the reduction. We have a separating. So in addition to the thickness reduction, the rolling usually again to increasing the width. Now, mainly because the volume is going to be the same. Okay, so the thickness initially multiplied by the initial width multiplied by the initial length is going to be equal to the final thickness multiplied by the final width multiplied by the final length. So if it's going to be the same, if that's going to be reduced, then the other should be increased, of course. So just basic analysis. Okay, just basic analysis we have here. You know that we're always going to have some mechanical issues going to be happened during the rolling process. So the velocity initially is going to be less than the velocity of the roller, and it's going to be this velocity is going to be both less than the velocity at the exit or the final velocities. So the rolls contact at the work along the arc defined by the angle theta, and each roll has a radius r. The radius of the roll is r, and its rotational speed is going to be given at surface velocity of the vr. It's more than the initial and less than the final velocity. Since the metal flow is going to be continuous, there will be a gradual change in the velocity of the work between the two rolls. However, there's one point along the arc where the velocity is going to be equal to the roll velocity, and this will be called the non-slip point. No-slip point, also known as the neutral point. On either side of this point, the slipping and the friction occurs between the roll and the work. And the amount of the slip between the rolls and the work can be measured by the amount of the forward slip. Yes. The true strain experienced by the work in rolling is going to be based before and after the stroke thickness. So basically, the true strain is going to be the natural logarithm of the initial thickness divided by the final thickness. So remember that this value should be more than 1. If you have this value is less than 1, then you are wrong. I'm not talking about strain, I'm talking about the TO over the TF. Then we can simply calculating the average flow stress applied to the work. The average flow stress, or the YF prime, is equal to the K multiplied by the true strain up to power n divided by 1 plus n. The average flow stress is going to be used to compute the estimates of the power and the force in the rolling. Friction in the rolling will occur with a certain coefficient of friction, and the compression force of the rollers multiplied by this coefficient of friction result in the friction force between the rollers and the work. Once in the entrance inside of the no-slip point, the friction force is going to be in one direction, and on the other side, it is on the opposite direction. However, the two forces are not going to be equal, and the friction force in the entrance side is going to be greater, so that the net force pulls the work throughout the rolls. We have to remember something. If we're going to have a hot rolling, this friction force will be simply going to increase. Now, there is a limit to the maximum possible draft that can be accomplished in the flat rolling with the given coefficient of friction of alpha of the friction, and defined by the equation that the D maximum, or the maximum draft, is going to be equal to the coefficient of friction square multiplied by the radius of the roller. This D maximum should be more than the actual draft. If not, then the operation is not going to be possible. The coefficient of friction in the rolling depends on the lubrication, the work materials, and the working temperature. In the cold rolling, the value is going to be around 0.1. If I'm going to increase the temperature to the warm working, the value is going to be around 0.2. It's going to be hot rolling, it's going to be equal to 0.4. The hot rolling is often going to be characterized by the condition that's called the sticking, in which the hot work surface adheres to the rolls over the contact arc. This condition occurs in the rolling of the steel at the high temperature alloys, and when sticking going to be occurs, the coefficient of friction is going to be as high as 0.7. Given the coefficient of friction sufficient to perform the rolling, the roll force F required to maintain the separation between the two rolls can be computed by the integrating of the unit roll pressure P over the roll work constant area W multiplied by the L. So the force can be approximated to be equal to the Y prime F multiplied by the W multiplied by the L, where the L is going to be computed by getting the R multiplied by the draft under square root. The torque for one roller can be estimated if I'm going to multiply half of the force multiplied by the length L. Torque is going to be in Newton meter. The force in Newton. The power required to drive each rolls is going to be the product of the torque and the angular velocity n for the pair rollers. So the power is going to be equal to the torque multiplied by the omega, and this can be equal to 2 pi n FL. The omega is going to be a radian per second. So if I'm going to have it in revolution per minute, I have to convert it to a radian per second. So now let's go back to the example and let's try to analyze the parameters given to us. We have 300 millimeter wide strip, 25 millimeter thick, is going to be fed through the rolling mill with 2 powered rolls. Each has a radius of 250 millimeters. The work thickness is going to be reduced to 22 millimeters in one pass at the roll speed of 50 revolution per minute. So you can see that we have the W, we have the TO, we have the R, we have the TF, and we have the N, okay, capital N, which is the RPM value. The work materials have the curve to be defined by the K of 275. I have the N to be 0.15, and I have the mu to be 0.12. We need to find first the maximum draft, the draft itself, and make a comparison. If yes, we can simply go to calculate the roll force F, the torque T, and the power P. So highlighting the parameters given to us, and we're going to have all the parameters to be highlighted, and this will be applied to the equations. So we start first to check what will be the value for the draft. Okay, so you can see that draft is going to be the initial thickness minus the final thickness. We have 25 minus 22, and this will be equal to 3 millimeters. That's easy. Now I would like to see if the maximum draft is going to be more than 3 millimeters. If yes, then that means that our parameters given can be do the rolling process. So the maximum possible draft for the given coefficient of friction is going to be calculated by the equation of the mu square multiplied by the R. Our mu was 0.12 and our R is 250 millimeters. So 0.12 square multiplied by 250, and this will give me 3.6 millimeters. 3.6 obviously is more than the 3, and thus we can say that the rolling operation is going to be feasible. Now we need to remind the rolling force. This is going to be equal to the y prime f and multiplied by w multiplied by the L. For us, we know what the value for the w. We need to calculate the L, and we need to calculate the y prime f. So these are the equations we're going to use to do the calculations. Now for the L, we know the R, we know the draft, we can calculate the L. For the mu value, which is true strain, we know the initial thickness and we know the final thickness, so we can find that. Then we can apply it to the equation for the y prime f to calculate the value for the y prime f, and then we are going to use these parameters to calculate the value for the force. So we're starting with the L. 250 multiplied by 3 under square root, this will give me 27.4. Now we calculate the true strain. The length of 25 divided by 22, and this will give me 0.128. Good. Now we're calculating the value for the y prime f, or the average flow stress. We know the K value. Now we know the value for the strain. The N is given, so we can apply these parameters, and this will tell me that the value for the flow stress, average flow stress, is equal to 175.7 megapascal. Now I have everything to find the value for the force, and this will give me that the value is equal to 1,444,000 786 Newton. Now I found the value for the force. I can find the value for the torque. So the torque, as we said, is going to be equal half multiplied by the F multiplied by the L. So the value for the F was calculated, as we mentioned, is 1,444,786. And that's to be multiplied by the 27.4 millimeters. And to change it to meters, we need to divide that by 1,000. So the answer is going to be 19,786 Newton meter is the answer. Now it's very important to remember that we have the value of the millimeters to be changed to meters. Then the power is going to be obtained by applying the parameters of the 2 pi and FL. It's going to be nice if you search how to convert the 50 revolution per minute into a radian per second. Okay, so we put everything in. To change the revolution per minute to radian per second, we multiply by 2 pi and divide by 60. Again, to leave it without divided by 60, this will give me the unit for the omega to be in radian per minute. So we have to change it to radian per second because the power is going to be in watt. So we multiply that by the force. We multiply that by the value of the L. And we end up that the power is going to be equal to 207,201 Newton meter over second, or it's watt. To convert that to horsepower, it's going to be equal to 278 horsepower. Okay, so that's it for the rolling. Okay, let's go back to the rest of the questions.